Okay, so let's start our colloquium today. We are very happy to have Rajdeep Sensarma from TIFR, and he will talk about many body localization. So I will hand it over to the speaker to start that off.
Thank you, Arpan, and it's a pleasure to give a colloquium at IIT Gandhinagar, although we are doing it virtually. And many thanks to Arpan for inviting me and giving me this opportunity to talk to all of you. So I'll be talking today about many body localization, and roughly speaking, we will give all the caveats later on, but it's a situation where quantum systems refuse to thermalize, and we will try to ask when does that happen, when that happens, how do we characterize those systems, can we see any of these in experiments, and so on and so forth. So let me get to an outline. So the first part will be almost like, elementary graduate course, or even sort of maybe a BSc course or something like that. I'll review a little bit about quantum systems in thermal equilibrium. And then we will start talking, this will be mostly to set up the problem. Then we will talk about thermalization in quantum systems, and we will talk about specifically a hypothesis called eigenstate thermalization hypothesis. So we will see what are some of the issues when people talk about thermalization, and at least one of the issues how this particular hypothesis, which came in the 1990s, tries to resolve. Then we will talk about quantum systems that do not thermalize. This would be about quantum systems that do thermalize. And that will be those systems we will put under a general rubric of many body localization. And when I talk about it, I will distinguish between what we call single particle localization, which is essentially a non-interacting system version of many body localization, and what we call many body localization, which is non-integrable interacting systems, but which still does not thermalize. Okay, and in this we will talk about two things. One, as we will see from the eigenstate thermalization hypothesis, systems which thermalize, their energy eigenstates actually have some very specific characteristics. Okay, so what we will try to ask is for things which do not thermalize, can we characterize the many body eigenstates, and in ways that distinguishes these many body eigenstates from systems which do thermalize. Okay, and we will see as we go on that at least on computers, you can create systems which easily go from behavior which looks like the system is thermalizing, and then you can tune parameters of the system, and the system will start not to thermalize and get into this many body localized phase. So that would be one part of the talk, and if I get time, what I will tell you is a little bit about how this lack of thermalization can be captured experimentally in terms of how systems retain memory of some initial states. So we will see how that does. So here, these characterizations are more theoretical in the sense that if you actually talk to an experimentalist and tell them, oh, I know this nice quantity or nice property of a many body eigenstate of a Hamiltonian of many particles, they would actually laugh at you, because there's no way for them to access a particular many body eigenstates, and we will talk about it. So so we will see one part of it, which is what you can do on computers. You will get a lot of numerical evidence for various things. And the other part, which will be directly related to experimentally measurable quantities, and how these two different ways of characterizing systems which do not thermalize. So that will be roughly the story for today. So let's go on and let's start at the basics. So it's a general view of dynamics. For example, if you have classical mechanics, you can write down Newton's laws. Uh, Mass times acceleration is force, or you can write down Hamilton's equations. Q dot is del H del P, P dot is minus del H del Q. And if you know what system you are talking about, for example, if you know what are the forces acting on a particle or what is the Hamiltonian of a system, this is something that classical mechanics does not tell you, and you have to go to whatever electrodynamics, nuclear physics, particle physics, and various things to know what your Hamiltonian is, what are the forces. But once you have knowledge of the system, then you can write down this set of equations, which is the equation for time evolution of quantities. Okay, but to solve these equations on top of it, you need what are called boundary conditions. You need to know, for example, the position and momentum of the particle at some initial time. And so knowing the Hamiltonian or forces is not enough. Knowing the system is not enough. You still need to know at least what happens to the system or where the system was at some initial time. Okay, that's what I would call a situation specific input, which is essentially boundary conditions. Once you have this, you can of course solve the problem. I have taken the simplest problem that you kind of solve. 1D harmonic oscillator. These I'm not going to talk in detail. I'm sure all of you know how to solve these Hamilton's equations for a 1D harmonic oscillator. What I would like to point out here is that if I draw the trajectories of the particle, this is a single 1D harmonic oscillator in the phase space, which is space of x and p. And what I have drawn, you will get ellipses. And I have drawn two ellipses with a black dot and a green dot. And these are the ellipses that the system will actually traverse. So this is the, for example, this will be the ellipse the system will traverse. If I give an initial condition, which is on the black dot, this is the ellipse that the system will traverse. If I give an initial condition, which is on the green dot. And so you see the simplest thing is that the trajectories and what happens in dynamics depends on initial conditions. I mean, this is as simple as saying, you know, if you are standing on a hill and if you are throwing a projectile, the angle at which you are throwing it, which is will tell you how far it will go before it hits the ground and so on. So yeah, everywhere, this is our common experience when we solve equations of motion for various things. We go on to quantum dynamics and we end up with a state, quantum state in some Hilbert space, psi of t. We end up with a Schrodinger equation, which says how the state evolves in time. But you act with the operator corresponding to the Hamiltonian of the system. So you get I del t psi of t is h times psi of t. Okay, and you can solve this problem exactly. You can take psi of t to be a to the power minus I h t psi 0. And again, you will need an initial condition, psi of 0, to solve this problem. We, of course, know from elementary quantum mechanics that life becomes simpler if you can write everything in the eigenbasis of the Hamiltonian, which are the states n with energy En. And then if you expand the state in this basis, you can find an easy answer for the coefficients of the state in this particular basis, which is Cn of t is Cn of 0 e to the power minus IE n t. And so here is your initial condition, Cn of 0, which specifies the initial state that you were in. Okay. And once you know all of this, you can go and ask what about observables, or which are of course operators A, and you can write down all the details. In the end, you will see that you need the matrix element of the operator between the energy eigenstates of the system and the initial conditions, and then you can write down a formula and then you can do your summations. Okay. If you want to take an example, the simplest example would be a two-state system, which is a spin half, which has two states plus and minus. And let's say there is a Hamiltonian which gives rise to an energy difference E between these two states. Maybe the spins are in a magnetic field. And you start with a state which is, a linear combination of plus and minus. And you ask for the value of the x component of the spin as a function of time, average of that. You can again write down all sorts of equations. So what you will see is essentially spin precession, that the spin will, if it starts from somewhere here, it will basically go like that and keep on moving like that. So that's the C0 and the C1 of T's will keep on evolving. However, I have drawn two pictures, one with the red arrow and one with the blue arrow, which denote the two different initial conditions. And of course, there are corresponding, circles that it will essentially keep tracking. If you write in this sphere, which is called a Bloch sphere. But what you see again is if I put the initial spin in different directions, I will actually get different trajectories, different values of Sx of t, for example. So in general, both in quantum and classical systems, there's some general idea that, what I get as a function of time depends on the initial conditions of the system. Now, that being said, we graduate from classical and quantum mechanics. We will be going through the syllabus of an undergraduate course in the initial part. So we graduate to thermodynamics. Okay, so what do we see? Here, thermodynamics is a macroscopic description. It's a phenomenological description of many body systems, systems which have many degrees of freedom. And it doesn't describe, however, the position and the momenta of all the particles. It describes macroscopic quantities like pressure and volume, magnetization and magnetic field, talks about temperature, talks about entropy, etc., etc. And these systems are in equilibrium. The important thing to remember is that there's no microscopic description of matter in thermodynamics. You actually do not write down a Hamiltonian. You usually need an equation of state, and if you are asking someone who is just doing thermodynamics where to get it, the answer will be from experiments or from some other sources. So thermodynamics per se does not care about writing down Hamiltonians of the system. However, it says some very, profound things. For example, it says that if I have a gas whose macroscopic coordinates or thermodynamic coordinates are pressure and volume, and I connect it to a system of spins, which is a magnet, whose thermodynamic coordinates are, let's say, the magnetic field and the magnetization. Okay, and I allow energy exchange between these two particles, then when I start, the pressure in the gas would be something, it would start changing. But if I keep this system on like this with, isolated from the environment, but only allowing energy exchange between the systems, claims that at long times, the pressure will stabilize to some value, the magnetization will stabilize to some value. And so things at long times do not change with time. The macroscopic variables do not change with time. And not only that, if you allow energy exchange, it says something more. It says there's some function of P and V, which is equal to some function of H and M, which should be equal in this long time state. And then that's what you can call the temperature of the system. This is what you would normally call the zeroth law of thermodynamics. If you move a little bit more, you define quantity called entropy. It's defined actually in thermodynamics in a very operational, but in some ways very complicated way. It says that you take a system from a point A to B through a process which you know to be reversible, which means you can go from if you can go from A to B, you can come back from B to A using the same process by reversing the energy inputs and so on and so forth. And then if you do it in two different ways, the change in the heat input divided by the temperature integrated over this process is the difference of entropy. It's something that does not depend on which path you take as long as both of them are reversible. Okay, so it's a formally well defined, but it's a bit of complicated definition that you go through to define entropy. And then, of course, you get the idea that if two systems which are isolated from everything else are allowed to equilibrium, that it reaches this long time state where nothing changes, the entropy, while exchanging energy between themselves, the entropy of the system will keep on increasing and is maximum in the final equilibrium state. Okay, so our other way of saying this is that spontaneous processes will lead to an increase in entropy of the system. This, of course, is known as, it's given various names: irreversibility, arrow of time, etc. It's basically saying that, you know, I'm starting, there's some quantity under the dynamics, it can only keep on increasing. Somehow the other motion which would lead to decrease of this is not allowed. Okay, or other kind of dynamics which is related to decrease of this quantity entropy of the whole system is not allowed. And but that's, so it says some very complicated but things which are, however, valid, seems to be valid for a very large class of systems. Okay. So that's where we start with the thermodynamics. So we started with dynamics, where we found that, you know, what happens depends on initial condition. The thermodynamics, which says that what happens kind of doesn't depend on initial condition. It does depend on a few variables, like maybe the total energy and so on, but not on the details of the initial conditions. And whatever you do, if you in the end reach equilibrium in an overall adiabatic sense, then the entropy of the system will keep on increasing. Okay, so that's thermodynamics. And the third thing, that third leg of all this is, of course, equilibrium quantum statistical mechanics, which is trying to explain how to write down thermodynamics, or how to compute or get thermodynamic quantities from a microscopic description, and using, let's say, the Hamiltonian of the system and so on. Okay, and this is prescription due to Gibbs and later, let's say, von Neumann, etc. And the idea is that you just think of multiple copies of the system, and which is called an ensemble or collection of the systems. And in each of these systems, you choose a particular, choose the system to be in some particular energy eigenstate n, but you choose it to be in n with a classical probability p equilibrium of n. And then you can simply average observables first over eigenstates, then over the classical distribution. You can write it in the density matrix operator language, and that's your average. And that's what you would measure in equilibrium. And just a point, because this will come back to us when we go and look at MBL. One thing I want you to keep in mind is that every density operator, whether it's equilibrium or not, can always be thought of as a process where you choose certain orthogonal states alpha. This may not be Hamiltonian eigenstates, with classical probability P alpha. So every density operator can be written like P alpha, alpha, alpha. And if you want to know what are the eigenvalues of this classical probability, so eigenvalues of a density operator are the classical probabilities, and eigenvectors are states which are chosen with those probabilities. This may not be Hamiltonian eigenstates, but every density operator can be written like this. So this is something to keep in mind. Eigenvalues are probabilities, eigenvectors are states which you choose with those probabilities. And then Gibbs gives you a prescription for equilibrium. Find P equilibrium of n. And that prescription is that you actually look at the von Neumann entropy of these classical probabilities, P eq n, okay, and equate it to the thermodynamic entropy of the system. And you basically find the equilibrium by maximizing this von Neumann entropy with respect to this. You treat P eq n as some sort of a variational parameter, and you maximize the entropy, and that gives you the equilibrium distribution. Okay, these are things that we learn more or less in early classes. This may be at the level of early graduate classes. And if you do it for systems with a fixed total energy, and this is something that will be important for us, you get to the microcanonical ensemble, which says that as long as the state has energy E, which is fixed, it has all of them, all those states have the same probability of being chosen, which is equal to 1 over the number of states with that energy. Okay, so you get equal probability for all eligible eigenstates. If you want to let energy fluctuate, you will get to your Boltzmann distributions and canonical ensembles. And the idea is that as a prescription, it's a highly successful program. If you don't ask many questions, you just shut up and calculate using this prescription, then for a very large class of many-body systems, you will actually get the correct answers. You will be able to match things with experiments and so on. So very successful program. And that's my review of and setting up of quantum statistical mechanics, if you wish. And if there are no questions, I would move on to now the uncomfortable part. This was the part that everybody understands and knows how to implement. So.
Hello.
Yeah.
So could you please explain that irreversibility and thermodynamic arrow of time? Like I can understand the sense, but
so it says that okay. So actually we'll come to that. So think of the following. Suppose I give you a Hamiltonian dynamics, okay, and you maybe go from a point here to a point here in time. Okay, maybe this is in some very high dimensional phase space. In general, if I reverse the time, like if I run the video backwards, it's an equally valid motion. Like if I start the system here with a velocity like that, instead of a system here with a velocity like that, it should basically follow and come back here. Okay, that's essentially what you mean by time reversal. You just try to run the video of the motion back and ask, would that have happened? Okay. And when you are saying entropy should keep increasing, then what you are saying is that no, this could not have. I mean, if the forward motion was increasing entropy, clearly if I run the video backwards, I would decrease the entropy. Okay, so somehow the video running backwards is not a valid motion, and that's irreversibility, if you wish. Okay.
thanks.
Yeah. Okay, so let's move a little bit to the uncomfortable questions. This very successful program, of course, is underpinned by some things which are still, I would say, not very satisfactorily answered. How does a dynamics which is manifestly reversible in time, which is the microscopic dynamics, lead to irreversibility in terms of this kind of macroscopic coordinates like entropy? This is not a question this is a question, important question. We will not talk a lot about this today. So the other question is, why do the detailed initial conditions not matter for thermodynamic quantities, right? In other cases, when we just looked at dynamics, it's in very detailed initial conditions mattered. You can ask, is this true for all quantities or is it true for some observables? Okay, You can ask questions like, if I just give you a quantum mechanics and a Hamiltonian dynamics, which is the unitary dynamics, will all closed quantum systems lead to a statistical mechanical equilibrium description at long times? This is a question we would be interested in asking. And if it does, are there special characteristics of those quantum systems which makes them look like they're described by an equilibrium statistical mechanics? And of course, then there is this famous question which we all ask, which is, where are the multiple copies or ensembles that we are using in Gibbs prescription coming from? I, of course, have only one experimental system to look at and measure. And the answer that you are usually given is that experimentally measurable quantities are averaged over times which are much, much greater than microscopic time scale. So when I'm measuring pressure, and the way I measure essentially averages over some large time scale like that. Okay. And then you make a very, very radical assumption. The system at different times explore all the different states. And the way it explores, if you average the quantity that you have measured over time, these contributions, this averaging is same as the ensemble averaging that Gibbs is asking you to do. Okay, that's the statement we keep on making. We say this started with Boltzmann trying to think about how to think of what are these ensembles. And you might have often heard this in the colloquial word, time average is equal to ensemble average. Okay, so here's what people mean. So forget about particles and Hamiltonians. Just think of a large number of people crossing a very busy junction every day. And say you are interested in the average number of friends people meet at the junction. Okay, so there are two ways to do. You can do the experiment for a large number of days and send one person, but just count the number of friends a single person meets. That's what you would call a time average. Or you could count the number of friends a large number of people meets, but do it in a day, in one shot, and that would be the ensemble average. And essentially, you are asking, if I have such things, when are these two things same? Okay, maybe for friends it's same, but maybe if you are looking at average number of accidents you are having at the junction, it's probably not the same, because if you have an accident, for example, you might die, and I cannot continue the experiment for the next days. So doing this experiment for a large number of days while you are having accidents at some rates, it can be issue. Whereas if I do it with a large number of people, I will probably not have these issues. So there are cases when these things can be same. There are cases when these things can be different. And the usual answer that you are given is that the dynamics, now coming back to the Hamiltonian and thermodynamics question, is that the dynamics has to be of a very special kind. From any typical initial condition, the system should explore all possible states. Let's say I have conserved energy, so I'm only talking about states with the same energy. And as you wait till infinite time, the system should be exploring all the possible states. Okay. What is more important in this case is what is called a property called mixing, that as you wait till infinity, the system has essentially equal probability to explore each of the available states. Then it's not surprising you will get the microcanonical ensemble. And that's the argument that you get in your standard statistical mechanics books. Now, these statements that are made are not wrong. If they are satisfied, you will get time averages, ensemble average, and so on. What is problematic is we will see in our next slide that they actually hide certain things about what the dynamics needs to be. Okay. So what's the problem with just saying, oh, I will explore all the states? So let's take a simple system. And you can make the argument for other systems also. I'm taking a simple system because it's easy for me to calculate and show you some things, but the arguments that I'm making are not dependent on me choosing a particular system like this. So you consider spins which have, let's say, spin half two-state systems on a lattice site. So each lattice site has a two-state system with, let's say, the total V or volume number of lattice sites. And let's assume the underlying Hamiltonian is something simple like a Heisenberg model. If you are nearest neighbors, then there is some spin-spin interaction, which is like Si dot Sj with a scale minus of j. Okay, so reasonably simple Hamiltonian. And you can ask how many states are there in the Hilbert space, and the number of states will be 2 to the power v, which will be e to the power v log 2. Okay, so it's exponential in the number of lattice sites. That's the important part. And you can now ask what is the lowest energy state of this system with this Hamiltonian. The state will be of the order of minus v times j when all the spins are aligned. There will be a factor corresponding to the number of nearest neighbors I have, which I have missed, but that's okay. That's not important for the argument I'm going to make. Similarly, the highest energy state, this will be the state where all the spins are doing, let's say, this. Okay, so highest energy state will be the other one. Let's say I'm doing this. Okay, so every bond is actually gives you a positive value of energy, and you will get a highest energy of state, which is v times j, ordered v times j. The main point is the range of energies that you are getting is scaling linearly with the system size. Okay, so that's important to keep in mind. Whereas the number of states scaled exponentially with the system size. And that means the average level spacing, if I ask, take EM and EM plus 1, the next state, okay, and take its difference and tell me what is the discretization between this on average. I mean, this will be different at different parts of the spectrum. You will basically see that this should scale e to the power minus v, which means that your states are really, really close in energy, at least somewhere in the middle of the spectrum they are. And how close they're exponentially in the small level spacing in the system size. As a result, you can ask how many states are there in some with dE, and that will scale as exponential of the system size because you are going to divide by the level spacing. And then you can ask, okay, I have a scale, energy scale j, which is basically the transition frequencies, because I have only one scale in the system, between the states will occur with the frequency j. Okay, so on a time scale of j inverse, I will make transitions. So how much time will be taken to visit all these states? I'm assuming that at the time I'm basically can make transition to maybe order v states, but not more than that. This would be exponentially large in the system size. So what does that mean? Let's try to calculate this number. And typical exchange scale in a system would be about, let's take it to be a gigahertz. Let's take v equal to 1000. Actually, we should take about 10 to the power 23, but let's take v equal to 1000. Let's take dE to be 0.001 j, which is in this case j divided by the number of sites. Okay, and you will see that t will be about 10 to the power 482 years. And I would like to remind you that the age of the universe is only 10 to the power 10 years, okay, approximately. So what this says is, if you really naively think that you are going to explore all states one by one, okay, and that's what is happening, then you would actually have to wait much, much larger than the age of universe. So such a thing might be true as a mathematical statement, but it will be completely useless for describing anything that we are looking at now in the universe. Okay, so it cannot be that the system actually explores all the states that are available to it, even when it thermalizes. So, okay, so what happens? So that question was first, people started answering this question. These two gentlemen.
Rajdeep, can I ask you a question?
Yeah, yeah.
So regarding the previous slide, so
Yeah.
suppose you have an infinite number of conservation laws. So how would this counting go? So the number of, so now you would have the states characterized by an infinite number of conserved quantities.
Yes.
So each such.
So you would have to calculate in each sector.
Yeah. So each such sector would have much less number of states. So you would also divide by much less number of states. So you would also divide by a smaller number.
So there you will be, because of the conservation laws, when I say transition to states, those will be curtailed. Many of those will be zero. So you will essentially only explore a sector of this. Okay. And now, if you really think that you have a 2 to the power n number of conservation laws, okay, then of course, there is very little dynamics that you can actually do. Even when you have a large number of, so that's what will stop you from doing this counting.
Yeah, so let us say I have some kind of play between the number of conserved quantities and the system size.
Yes.
And I'm just wondering whether this time calculation, how would this, so I mean, of course, because there is broken ergodicity, so what you say is, of course, correct, that in any finite amount of time, you would explore much less than the total phase space. But now, so now with
suppose you have,
suppose
you have number of conserved quantities which scales with the size of the system. Let's say V, not exponential, but size of the system, right? Then okay.
Then it would remain the same.
Yeah, and then but you will just get to this whatever Gibbs generalized Gibbs ensemble, because you cannot explore everything. But that counting will remain same. But that will tell you that even in that sector, if you are really thermalizing and looking at experimental observables in a reasonable amount of time, okay, then there's something more that is happening in that sector. It's not just that counting will still give you numbers which are very, very large.
Yeah, I guess so. I have not done this counting before. Yeah. This question just arose in my mind.
Yeah, yeah. So it's very hard to beat the exponential. It's a problem.
Yeah.
Yeah. As we are finding out in Mumbai nowadays, it's very hard to beat the exponential.
But means if the Hamiltonian is very non-local, is there a chance of exploring? Means
if you, yeah, okay. So let's not get into very non-local Hamiltonians and so on. So for example, these kind of calculation which say that this is V times J, assume that I have a very local Hamiltonian. So this energy calculation will not remain true if you have a very non-local Hamiltonian. Then depends on how non-local and which way you are going.
So means in SYK what happens? I'm just asking, means in SYK does it?
SYK, it's a complicated business. So what happens is that the statement that I made in a general system is true in the middle of the spectrum. Okay. Whereas if you come close to a ground state, this statement is not true. Ground states are atypical states. Okay. So for example, if you have a Heisenberg model, and then you will have spin wave states, which will scale as 1 over L and not exponential of minus L. The energies will not scale like that. Okay. So the point being that those are not in the middle of the spectrum. Whereas in SYK, that whole thing continues all the way down to the ground state because of the fact that it's a very non-local, etc., etc. Okay, so that's a difference. In fact, SYK, what you are getting here goes all the way down to the ground state or very close to the ground
I
state.
see, I see. Okay. Okay.
Okay. So Srednicki and Deutsch started basically this, they try to find a resolution which is known as the eigenstate thermalization hypothesis. And what they did is, the first thing I have done here, which is what they did, is write down what would you get out of standard quantum dynamics. I mean, this is exactly what we had written in the first or second slide. So and then you ask, okay, if I'm happy to average over some time scale from 0 to tau, what happens to this quantity? And the first thing that you see is, for the terms where n equal to m, there is no phase factor. So they would just go all the way, because I am integrating from 0 to tau, I'm dividing by 1 over tau, they will just come up. What about the terms with the phase? Okay, so these off-diagonal terms, n not equal to m, will integrate to 0 if your integration range of time is much, much greater than em minus en inverse. Okay, that's what will happen. But now you have this coming back to the same problem, that the gap em minus en is basically exponentially small. So you would have to wait for exponentially large amount of time, which is going exponentially large with the system size, for the off-diagonal elements to actually wash out. Okay, so this is the problem that we had earlier. This is just come now in a different guise. And so the resolution was that, for kind of operators you are interested in measuring, let's call them all local operators, and OMN, which is the off-diagonal element, which is what is giving you all these phase oscillations, is 0. Or 0 means it's small, it's exponentially small if m is not equal to n, and when em and en are in the same energy window, very close energy window. Okay, so you're saying, forget about this getting 0 from this integral, I'm telling you this is 0 essentially. Okay, and then we do not need to integrate for exponentially large amount of time, because there's exponentially small quantity sitting here, and that allows us to look at reasonable times and still say that I have a diagonal number here. I do not have the off-diagonal pieces. Okay. So of course, will this reproduce results from microcanonical ensemble? You need a little bit more. You have got a diagonal bit, but what you want is the coefficient Cn squared to be constant, because you said it's equal probability of all of them. And you want this to be 1 over omega E. And that was the ETH solution. We said that, well, first of all, you get a delta Mn, but even that, even the diagonal matrix element, A has a smooth function of E, which means it does not vary from one state to another as long as E is the same. It's not completely true that it does not vary. It can vary, but it should vary by only an exponentially small quantity. So that the term which depends on which state I'm looking at should go with a e to the power minus v, where v is the system size. Okay. And then the long time average of O will follow the microcanonical ensemble average for fixed E, because these terms, what will happen is, you have to be careful because there is an exponential number of them, but their number, you are also seeing that each one is exponentially small and so on. In fact, what you need is a more important thing. You need the variance of this over the same energy state to scale with exponential of minus v, and then you can think of fluctuating the energy in the usual sense, and also get a canonical ensemble. I'm not going to do that construction carefully here, but that's what the ETH says. It says something very strange. It says that if you have to thermalize within a reasonable time, the energy eigenstates must have very special characteristics. For local operators and energy eigenstates which are close in energy, off-diagonal matrix elements must be exponentially small in system size, and the diagonal elements are same up to variations which are exponentially small in system size. Okay, so you're saying that if you have this, then you do not need to go wait for exponentially large times. You will get microcanonical ensemble. as soon as you average over timescales reasonably large. So that's what is called the ETH, and that's how you resolve the problem with the ergodic hypothesis. Okay, so let me now, in the few moments, I will probably only talk about the first one and not the second one, because we are already at maybe.
Could you please go back to two more slides? Two slides back.
2 slides back.
Yeah. Yeah. How like off diagonal terms integrate to 0? I mean.
Oh, because if
Okay.
I integrate just e to the power I omega t over some scale which is much larger than omega, will average to 0 essentially.
Yeah, I got it.
Okay. Okay, so now let's get to the matter of the.
Hello.
Yeah.
Sorry, I have one question. So you started with a pure state which is psi, and then somehow you are telling that after a long time it will thermalize.
Yes.
So that's the thing I did not understand. You started with a pure state, how it comes to.
So it didn't say that your state went to a density matrix, which it will not. It said if you have this kind of operators, their expectation values, time average expectation values, will look as if they have come from an ensemble average with a density matrix. These two statements are not the same, right? One is ETH does not tell that the state of the system has become the density matrix. It says if you are, however, measuring local operators, it will look that they are coming from a density matrix. So that's how it resolves the issue.
Okay, thank you.
Okay, so then the next question is, okay, are there systems which do not thermalize, which let's say do not follow ETH and so on? So we know two kinds of systems. One are called integrable systems, which is what, for example, Gautam was talking about, large number of conserved quantities. And I will not talk about it. Gautam is, of course, an expert on this, and you should ask him to give a talk if you want to know about these things. I will talk about non-integrable systems, which are systems where the couplings like interactions or various things will be random. They are random numbers. They're drawn from some probability distribution. This is what we will call disordered systems. And in general, I will try to think of couplings which are not only random, but they also have very large variances. Okay, which means they are fluctuating quite a bit as I go from one realization to another realization. And these kind of systems may also not thermalize, which is more new and which is the subject of many body localization. Okay, so how do we think about it? Actually, Anderson thought about it way back in 1958, and he was talking about strongly disordered systems, say electrons which are moving in some potential, but the potential is some random thing. Okay, the claim is that it's strongly disordered systems behave qualitatively differently from typical many body systems we learn about in stat mech textbooks. For example, there's no transport. If you try to take this very random electrons moving in this very strongly random potential, and you try to tilt the thing by an electric field, you will not get a current out at the other end. Okay, so that's like the transport, at least not in the thermodynamic limit. That's absence of transport. You will see that the system will not be able to act as its own heat bath. By that, it means that, one part of this, if you are looking at a small subsystem out of this system, the rest of the system doesn't look like as if it's providing its heat bath with which it can, exchange energies and go thermalize and so on. So, and that essentially leads to the absence of thermalization. Okay. So if you are doing this in a non-interacting system, this is called Anderson localization, worked out by Anderson in 1958. There's a very nice review article by Patrick Lee, T.V. Ramakrishnan, and others, and reviews of modern physics. However, the thing that we are interested in is we want to do this, but we also want to have particles interacting with each other. This is called many-body localization. That's how we will differentiate it from Anderson localization. And there's a bunch of references, and by now the references have grown. There are, all these are reviews now at this point, and which has grown over the last maybe 10 years, starting from 2010 around, and it has become a big field. So what happened? So let's go. I'm going back to one of the early papers, which was by Arijit Pal and David Hughes in 2010. And what they did was they provided numerical evidence. And what they did is they took a Hamiltonian, which is a one-dimensional Hamiltonian, which is the kind of Hamiltonian that I wrote down, J times SI dot SI plus 1, which is a Heisenberg Hamiltonian. But on top of it, they said they will, each site has a random field HI, which acts on the SZ of I. Okay, and they basically took this to be some uniform distribution between minus H and plus H. Okay, so this is how the probability distribution, which means, if I keep on increasing H, I am basically increasing the variance of these random variables HIs. They are independent random variables and so on. And what they did is they diagonalized this Hamiltonian on a computer. They calculated, let's say, the difference of local magnetization between successive energy states. So you take a energy state E, you take the next higher energy eigenstate, you calculate local magnetization M of I or SZ of I in these two states, subtract it, take a mod so that you don't, and then you sum over all various states and you ask what happens to this quantity. Okay, that's what they were plotting. And this is plotted on a log scale. So this part is the log of that. And at low disorder, what you saw, and this is done for different system sizes, what you saw is that exponential decay of this difference between successive eigenstates, which means the eigenstates did follow ETH as far as this particular observable was concerned. And in the same, so these you can see disorder strengths. J is set to 1, I guess. H is about 0.6, 1.0, etc. Whereas if you go to high disorder, you see that the differences are weakly varying with system size. There's no exponential decay, and your eigenstates violate ETH. So not only did you show that systems can be both ergodic or thermal and MBL, and when I say ergodic, I mean in the ETH sense, but they also showed that you can make a transition from one to other as a function of disorder. Okay, so that's the big impact of this paper in 2010. So then people started asking, are there other distinguishing features of the energy eigenstates, and can I see them changing across this transition? Okay, so this was first that it didn't follow ETH. So people did many such calculations. For example, here is statistics of energy gaps. So what they're taking is they're taking the difference between the energy eigenvalues between successive eigenstates, calling it the gap between the two states. These are the many-body energies. And then taking mod and calculating this quantity R, which is minimum over maximum. And again, they're plotting the average of this quantity here as a function of H. At low H, you see that you actually have an answer which comes if the distribution is what is known as the Wigner-Dyson distribution, which comes from a random matrix theory, which is essentially what happens to the gaps in a matrix whose entries are uncorrelated Gaussian random variables, with particular this portion. And so uncorrelated Gaussian random variables. And out of that, if you do all these calculations, you should expect an average value of 0.53, and you can see here that it kind of went to 0.53 at low. So this is about 0.53. Whereas when you went to very large disorder, the distribution of these objects became Poissonian, and that gave you an average of 0.39, and you can see this transitioning from this 0.53 to 0.39. This is a broad transition between ergodic and MBL phases. Okay, so
one
having that, yeah.
in that plot, many of these lines seem to cross near one
Yeah.
point. Is there anything special about that point?
Yeah, I mean, in the sense, well, it's kind of, I mean, normally if you are thinking of a phase transition and if you are drawing order parameter plots, you would see some crossings, but these crossings are not exact. These crossings do tend to drift, even if you, although it looks like they're all crossing here, if I take successive crossings, the crossings will be drifting in the value of h as I change. Now that could be simply because you have not gone large enough L, or it could be it's not a phase transition, but some sort of a broad, crossover.
So it's almost always a broad crossover in these.
As far as this is going on. So let's see what it does a little bit later. Okay, so just to give you a very brief primer on if you take a state which is on this big lattice, and if you want to basically say that, okay, I do not want to know what is happening to all the degrees of freedom which are in this B subsystem. You break it into two subsystem A and B. Let's say I have spins here, I have spins here, and I'm saying that I don't want to know about the information of the B subsystem. Then what you can do is you can trace over those degrees of freedom in quantum mechanical sense. And then a single eigenstate will now look like a density matrix, but living only in the Hilbert space of A. And that object is called a reduced density matrix. One way of thinking about, as I said, density matrices is to think of choosing quantum states with classical probabilities. So the tracing converts a pure states to density matrices or exchanges somewhat quantum amplitudes for classical probabilities and so on and so forth. If you, for example, have just two spins and you trace over, you take this singlet state, you trace over the second spin, you will get a matrix which is half zero, half zero, half, okay, diagonal. So next thing is, what is entanglement? Well, you know that there's something called Schmidt decomposition, which means every state can be written as a product of states living in A and B, but not just as a product of states, but sum over them with some coefficients. This, I guess, should be alpha I, given what I'm writing next. And if you know how to do this decomposition, then you also know what the density of matrix you will get. You will get simply alpha I squared times psi IA, which is again like the same thing, choosing the states psi IA with probability pi. Okay, so that's. Now, however, you can ask what are the PIs I am getting for a particular state, and if PI is 1 for one state and 0 for all other states, which means rho A is essentially a pure quantum state, then the reduced matrix, so the original state is then called separable or factorizable, and this is not entangled. And entanglement is basically when you do not have this, when you do this tracing business and you end up with more than one PIs which are finite, okay, then you will say the original state is entangled and the tracing leads to classical probabilities. A couple of definitions before I just tell you what we did. So what happened is that you can take each of these eigenvalues of the density matrix, okay, and instead of that eigenvalue, look at minus log of pi. If you are more careful, you can think of a density matrix as exponential of minus HE. And it's then the spectrum of HE, if you wish. Okay, so that object is called entanglement spectrum. So take all the eigenvalues of the density matrix that you get, reduced density matrix, take its log, take a minus sign, and that's it, is the entanglement spectrum. If you take this classical distribution and calculate its von Neumann entropy, that's called the entanglement entropy. Okay, and before we move, let's look at the special case which we had, where I ended up with a factorizable state. So the corresponding lambda I is 0, pi is 1, SA will be 0, so the separable state has 0 entanglement entropy. You can take another special case, which is nice. which is that only two states have P1 equal to P2 equal to half, and every Pi is 0 otherwise. Okay, which is a density matrix like this. There is a qubit space, two-state space, where it's maximally entangled, half, 0, 0, half, and 0 otherwise. Okay, note that if I just said P2 is half, okay, this would actually be same as P1 is half, because P1 by definition has to be larger than or equal to P2. And so if P2 is half, the only thing P1 can do is also be half. Okay, or equivalently, I could have said if lambda 2 is log 2, I will get this maximally entangled qubit space. The other case to consider is when you have 1 over 2 to the power LA all the way down. And this is maximally entangled in the full Hilbert space of A. And in this case, the entanglement entropy scales linearly with the subsystem size. It's LA log 2. Okay. Now, with this in mind, let me just go quickly through what happens when you use this kind of measures to distinguish the energy eigenstates. This is from Paul and Hughes's paper again. So what happens is that if you are at a very high disorder, entanglement entropy does not change with the system size. This is called an area law. It basically says it scales as L to the power d minus 1, which in 1D is L to the power 0. On the other hand, if you are at weak disorder, it seems to be scaling with the size of the subsystem, and that is called the volume law. So that's another distinguishing features between the energy eigenstates of ergodic and MBL states. People ask the question, can you look at the distribution of all these eigenvalues? Why just look at the entropy? You have all these eigenvalues. Let's look at all the distributions. So here is Nandkishore et al. Who looked at distribution of all eigenvalues. Okay, and their claim was that if you have a weak disorder, you have a unimodal distribution, a single peak, whereas when you have an MBL, you basically have a big peak at 0, and then there is another thing happening at a finite lambda. Okay, I will not talk about this. These are some cases where people looked at extremal eigenvalues instead of looking at all the eigenvalues. Maybe we look at the initial few eigenvalues. Here, for example, people have ordered it in K, and this is the largest eigenvalue, next largest eigenvalue, and they have plotted some averages and so on and so forth. Okay. So what we did, and this is a very, so let's see what we did within this. We found another way to characterize the eigenstates of ergodic versus sort of MBL phases. Again, we are using the same Hamiltonians, so and so on. So what we did is we looked at the lowest entanglement spectrum, which means I take a density matrix, I look at its highest eigenvalue, and then I take the minus log of that, that is the lowest entanglement spectrum, and I look for its distribution. Okay, this is for different system sizes at a low disorder, and what you see is that the distribution changes as you change the system size, and there is a peak in this distribution, which is roughly at the log L. If you track how the peak changes as log L as I change the system size, and that's the distribution. So the Mech, the peak is happening at some finite value of lambda, or some in general value of P in general. You go to high disorder, the same distribution. This is, however, plotted in a log scale. Looks very different. At low lambda, which means we are looking at eigenvalues which are very high and close to 1. Remember, eigenvalues are probabilities, they cannot be larger than 1. So we are looking at getting eigenvalues which are very close to 1. You see that the distribution is a power law. This is for 3 different high value of the disorder. P lambda 1 goes to lambda 1 to minus B. There's a kink exactly at log 2. And then beyond log 2, if you ask what is the distribution looking like, It's not clear here, but I can assure you that it looks like an exponential distribution. So it's more complicated than what is happening here. There's a power law at low lambda. There's exponential at large lambda. There's a kink at log 2. And so the question is, can these distributions be now used to identify, for example, the transitions, or whether you are going from MBL and ergodic? And here is your transition.
One question before this means was it true that if you look at the average value, then there is no L dependence? Only if you look at the
average value of one
of lambda
yeah. So in fact, in fact, I did not put the graph here. Even the whole distribution is pretty L independent. It's not just the average. It's the distribution in this limit. Things do not depend on system size.
Oh, I see. Okay.
So even the full distribution is quite invariant.
Yeah, Rajdeep, I have another question, which is that in all of these things like the entanglement spectrum, you do it for a particular realization of the of this J's, or do you do a quenched average of some quantity after? So
I'll tell you exactly what I do. My disorder is in H. So first I take a realization of H. Okay. In this realization of H, I get many eigenstates, of course. Okay.
Right.
So for each eigenstate, I construct the density matrix. And from that density matrix, I get one lowest entanglement spectrum. Okay. So first, I average over all states with the same disorder realization. When I say average, I don't average. I mean, I bin all the data from all the energy eigenstates.
Good.
And then I take different realizations and then bin all those data together to get my distribution.
So, so you don't. Okay, so you mean that you bin them together? So I'm just wondering what quantity do you average? Like, you know, there is in quenched averaging, there is a notion of averaging over log z. So you compute the log of the partition function, and then you you know.
First of all, this is not observable. So
yeah, that's what I meant. So then, what is
actually? We are actually looking at distributions and not averages.
So
it has much more information than an average.
No. The averaging, I mean, only over your H, the random variable. That's what I mean.
So that's what I'm saying. If you take different values of H, so you can ask, if you take different realizations of H, for each one, you will get some bin, some frequency in a particular range. Okay. And then you bin all of them to get the distribution of lambda 1.
Okay. So
for
you
example,
you just combine them into together.
So there is a binning over the energy eigenstates, which is from in the middle of the spectrum, and then you take another another realization and you bin again. But what we have seen is that, you know, at these high H's, it actually does not matter. Even if you bind for a very few realizations, but bind over eigenstate, the distribution looks pretty similar. So it's not like the distribution. Of course, binding over eigenstates improves your statistics, but other than that, these answers do not fluctuate a lot if you.
I see. So it's not kind of self-averaging over at least over the distribution of H.
The distribution, as far as the distribution is concerned.
Okay, thank you. Yep.
Okay, so the transition is basically, you see, this is the power law going down, large H. You are going down in H, and at low H, you are having something which is the single peak. And at every point, you can fit, because you have a log 2 as a natural cutoff, you just fit this data. Okay, and fit B out of it, and then plot that B as a function of H, and that B goes from positive at very large H, which is this is decaying, to negative at small h, And so at some point it goes through 0, and that crossing point, a claim looks like the transition point, or can be a proxy of the transition point. And you can ask how much does that change with the sort of system size, and the answer is not much. Okay. So if you take the old data of R values, which are this broad distribution or crossover, this is where this change is, and the errors are very small around this point. Okay.
And
so
is there any reason why you chose the lowest eigenvalue?
Well, in some sense, MBL, if you are going to MBL, you are going to go to something where, things are kind of unentangled, which means PI should be close to 1. So then it makes sense to look at the largest PIs, even if they are not 1, and say how far they are and what their distribution is.
But if you looked at some other lambda, you would have got the same critical B.
Wait for one slide. Okay, so we did look at the second lowest entanglement spectrum, and then we had some more interesting stuff. So here is again, if you look at low disorder, the distributions are pretty, okay, I mean, they're not same, but they look very similar. However, if you go to high disorder, and this is, I think, at 8 or something, H of 8. Okay, what you see is I have plotted P2 of lambda 2. Now lambda 2, realize that P2 has to be less than half by definition. It cannot be greater than half, which means that lambda 2 should be greater than log 2. Okay, so now you plot the distribution. This is for, again, Deeptarko just showing for different strength, system sizes, things don't change much. And what you see is that if you look at log 2, the P of log lambda 2 equal to log 2 is finite. Okay, just to remind you, log 2 is somewhere here, so P of lambda 2 to log 2 is 0 here. Okay, so we then asked what happens as you go through the transition, and this is what happens, 6, 4, then you go to 2, it goes down, and then it goes to 0. Okay, and so you can ask, can I take the point where P of lambda 2 equal to log 2 goes to 0? Remember, when I have lambda 2 equal to log 2 or P1 equal to P2 equal to half, that's the point. So I essentially have within my subsystem a maximally entangled single qubit. That's my density matrix. Okay. What these qubit states are, they're probably not local spins, there's probably some complicated stuff, but what you know is that it has support only over 2 states and with a half and half. Okay, and if you take this point and you plot it on the same graph, you see something which is very close to the earlier point that you have gotten. So in general, you end up with, by looking at the distribution of the lowest entanglement spectra, you end up getting a sense of 2 things. One is that they will look very different in the MBL and ergodic phase. And if you use them to track transitions, now I should be careful because you have gone only up to L equal to 16. So if you ask what happens at L equal to 1000, whether there's a drift, there's no way of knowing at this point. But to the extent it is doable, people can, these are the numerical things people look at. So this seems to give you a very tight number on the transition point. And so it's weak L dependence and so on and so forth. So let me summarize. I have showed you that strongly disordered interacting quantum systems do not thermalize. They can be tuned from thermal ergodic behavior to MBL by tuning disorder strength. I have shown that energy eigenstates in MBL phase can be distinguished from energy eigenstates in the ergodic phase because they have very different characters, violation of ETAs, partial level statistics, area law entanglement, etc. And we have added a couple of things to it. lowest entanglement spectrum has a power law distribution whose exponent vanishing of its exponent characterizes the transition point, and vanishing of the second, you are looking for the probability of getting a maximally entangled qubit in your state, and when that vanishes, that tracks also seems to track the transition with weak L dependence. So this work actually was done with Abhishek Samanta, who is my student and who is now in Technion, and Kedar Damle, who is a colleague at TIFR. I think I'm way over time, so I will stop talking about the other thing, which is, can we see any of this in experiments? Because, you know, as I said, if you tell an experimentalist about energy eigenstates, but that's maybe for some other day. Okay, so let me ignore all of that stuff, and just to maybe one line to show you is that people can, what they do is they measure how systems retain memory. So they put systems, initialize systems with, you know, one particle on some sites, 0 particles on other sites, and let them evolve. And the Hamiltonian does not distinguish between these two. And they keep on measuring whether the system is thermalized, you know, density in these A and A bar sites would be same. If they have not, it will be different. And so that's what they keep measuring the difference as an imbalance. And just to show you one data without going into anything, you can, delta is some disorder strength. At very high disorder, you see that it goes to a finite value. At 0 disorder, it goes to 0. And so you can actually experimentally see MBL, not in terms of many eigenstates, but in terms of something else. But let's not get into those details. And just to point out that using sort of non-equilibrium quantum field theory type calculations, we can actually calculate these kind of sort of imbalances as a function of time and see finite imbalances. Work done with Ahana Chakrabarti and Pranay Gorantla. And this is actually a data I'm very proud of. It came out yesterday. A student of mine, Mursalin Islam, who has been working on this, has done some 2 differs. He can actually go up to 400 times the microscopic time scale and see a clear you know, imbalance going to a finite value with a very 2D force calculation. So, but I will not talk about this. I'll just come to the last slide. Collaborators on this work on entanglement is Abhishek Samanta and Kedar Damle. On the work on looking at imbalance was Hana Chakrabarti, who is again now a postdoc at Dresden, Pranay Grantla, who is now a PhD student at Princeton, and Mursalin Islam, who is at TIFR. So I'll stop here.
So thanks for the wonderful talk. And if anyone has any questions, please ask.
So if I might, so Rajdeep, so the second eigenvalue P2,
yeah,
if it is very low, like you know, very close to 0, that basically means that the system is almost a pure state.
Yes,
right? Because that would mean
that's
that
true.
P1
That's true.
is very close to 1.
That's
so
true.
Meaning that that end of the lambda 2, I mean, sorry, the P2 spectrum is exploring states which are like pure states, which are very different.
No, so there is a little bit of catch in here, because I'll tell you. Because you could have asked me, you know, why don't you look at lambda 1 equal to 0, which is as close as you can get, okay? And ask when P of lambda 1 equal to 0 has gone to 0. This is clearly diminishing, right, with disorder. And that would tell you that then you have no probability of getting a pure state.
Yes.
Right? So if you do that,
you mean then it just says that the entanglement is 0 as you expect? And that's what it means.
Yeah. So you're saying when is the, see, everything is probability. You're asking when is the probability that you have a completely unentangled state going to 0. Okay. Now you would have thought that would give you a reasonable answer to the transition point. But if you do this point, it turns out to be somewhere here. Not somewhere in the middle of the spectrum. It turns out to be the point where this thing starts deviating from the ergodic value, but it is way off from the middle of the transition region. So actually, I probably have the data somewhere. The whole thing decided to get to a dashboard of CoWIN. I don't know why.
It's going into some CoWIN thing.
Yeah. So for example, yeah. So these two are very close. That object would be somewhere here, okay, where it starts deviating. So you would have thought that that's what, I mean, that was our first, guess that that's what we should look at. Whereas what it seems to be saying is that this point is basically, this probability is essentially saying that you are exchanging one bit of information with B subsystem, right? Because that's what this P1 equal to P2 equal to half will tell you, that you are exactly exchanging exactly one bit of information. Okay.
Yes.
And what you're saying is that, of course, you can exchange more than one bit of information in a thermal phase. Okay.
Yes.
You would in general expect order of LA bits of information being exchanged. Okay. So, and in the MBL phase, there will be always some probability for exchanging one bit of information. There will be a probability for exchanging no information, which is,
Right.
What it seems to suggest is that, it's exactly when the probability of exchanging one bit of information goes to 0. That seems to be somewhere which is in the, so other way of saying is that I guess you can ask what is the eigenstate that is exchanging this information.
Right.
Okay? And so one way to think about this point is that, you have this, so let's say you have this cut. And what you are doing is you are exchanging one singlet bond across this cut. That will give you a log2, exactly. Okay. Now, this is not as I have drawn. You are not exchanging with a spin, but you are exchanging with a very complicated state in B and a complicated state in A, right? So, however, with those transform spins, all you are saying is I have one singlet bond between these two. And when I take that probability to go to 0, that's exactly where it seems to be the middle of the transition.
I see.
Whereas to say that I have, completely just factorizable states, that's not the start of the transition. That's somewhere here, essentially.
I see. Great. Yeah. Okay. So I'll ask you more.
Sure.
Yeah. Thanks.
I think maybe one last from my end. I think a nice question is that how like telltale is the signature of this behavior in terms of this entanglement spectrum? Means is there any counter example where this there is a power law in of spectrum, entanglement spectrum, but it's not MBL?
I don't know of one. I mean, there are all these other states which actually, I don't know if Subrata has left. Subrata is a much more bigger expert on those kind of states, which is, things where you might have one versus not the other. Like, you might have ETH violation, but not large entanglement and stuff like that. sorry, have largish entanglement. Yeah, to the extent I have seen, I mean, so now the question, of course, you can ask is that, what will you call this state?
Hmm.
Right? Yeah. If you fit a B, you will get a B. Should you
Right.
call the? Yeah, I mean, so sorry. In fact, I'm not looking at. So let's look at this. It still looks on a log scale a pretty straight line. Now, question is how straight is that straight line? Here, I'm not so sure. Right? And I have the nicest thing about this data. I mean, we have done all this kind of, which I didn't put here, which is change the range over which you are fitting and all such things. That seems to be in the critical region with a L equal to 16. What you are going to call it?
So
I can show you how much it, if you fit, you get a reasonable fit, and I can show you how much it changes if you change L. But I'm changing it only up to 16. You can say what happens if you went to 1000, and I don't know.
That was what I was going to ask. So is L equal to 16 is enough?
No, probably not. But I mean, people have done similar data up to L equal to 20, 24. It's
I see.
Up to that, it's okay. But beyond a point, I mean, you have to ask.
I see.
At least you're not going to settle that by numerics, is my general feeling. I mean, even if you go up to whatever, 30, you will always have this question, but should I have gone to 50 and seen something different?
I see.
I think the other way, Gautam, of looking at this one bit of information is you can ask over what length scale you are exchanging information, or how many, and one bit is like exchanging it over some effective lattice scale of 1,
right,
going across the cut. And it seems that once you reach that, after that, it's like a flow. If you think of some RG, this length scale flows to very large values. So whereas if you are less than 1, it kind of flows to 0. It's a very vague statement I'm making. I'm not making a very precise statement, but that's a kind of thing it looks like that one sets the scale.
It's like that. It's like the last step in a Wilsonian decimation thing. That if you have just 2 lattice points, that's it. You can't go down any further. Yeah. So yeah.
I mean, there should be a way of writing it effectively like that. We have not completely figured that part out. Partly because it states in the middle of the spectrum, anything you can do in usual Wilsonian energy will not. I mean, constructing the Wilsonian energy for this would be hard because you're not looking at low energy states per se.
Yeah.
So, but it is very kind of telling. But I mean, people have tried to write down RGs, to be fair, but how to then incorporate? There's work by Ehud Altman and others who have looked at trying to write down effective RG for this kind of thing.
So how does, if you look at 2-point function sitting at this kind of disordered state, does it keep oscillating, or means is there any signature with
dynamics?
Yeah, no, not dynamics, just the spatial. With you take the measure magnetization and keep separating it.
Because there's no ordering that is happening. In fact, people explicitly break all symmetries in the Hamiltonian so that symmetries do not play much of a role here. I mean, the whole idea is people don't want to deal with complications that might come from having symmetries.
Right, but this log 2 entanglement, will it have any signature in any correlation function?
I have not seen anything that will tell me that.
Or means anything can anything be said about matrix elements? Any statement like ETH for disordered states?
The problem is that then you are asking for not only the eigenvalues but the eigenvectors of this. And around that, we have not yet found anything which tells me that the eigenvectors are suddenly very different. That may be because we were not looking at the correct quantity. I mean, one way what you were saying would be to say that, you look at the eigenvectors, and something in the eigenvectors would keep changing. I mean, people do this local like people do, SI plus 1, and then take its difference between successive states, but not in a particular state. I'm asking what happens.
Yeah.